now on, that's got to be your habit, right? You got to tell me start recording, Tony, because Tony is going nuts doing this multiple times. Let me tell you. All right, so we got recording on this time. You guys online, that same thing for you guys online. If you see that recording button is not on, let me know. So at any rate, good. So we're going to do an exercise, and what this exercise is going to demonstrate to us is something about the dynamics of sampling from a population. Now, we've already mentioned that when you're dealing with biostatistics, when you're dealing with a lot of kind of data set, with that large data sets that we're dealing with, and large populations in public health you're dealing with, that most of the time you don't know everything about the entire population. We don't know the blood pressure of every student in Hunter. We don't know the weight of every student in Hunter. We don't know the diabetes status of every person in New York City, right? The only way that we learn about or can grasp what the nature of a disease, a condition, a physical parameter is for a population is by sampling it. That's why we're always talking about independent random samples, because those kind of samples give us a lot of information about the population. I can't afford to go out and test everybody's blood pressure in New York City, but I might be able to go out and randomly sample 100 people in the Bronx and 100 people in Brooklyn and 100 people in Queens and 100 people in Staten Island and so on and so forth. Problem is that I need to know how close that gets me to what I really need to know about the true population. I don't really care about, for instance, let's say the average blood pressure. I'm interested in knowing what the average blood pressure is of all the people in Brooklyn or all the people in Queens. Now, I can go out and I can take a random sample of 100 people in Brooklyn, 100 people in Queens. The question now is, when I get that result, if I take that 100 sample, 100 people, those 100 numbers, and I average them, what kind of confidence do I have that the number I wind up with, the mean from the sample I wind up with, is really the same as the population mean? Well, for starters, right off the bat, I can guarantee you it's not exactly the same, right? What would be the odds of taking 100 people and getting exactly the population mean for the entire borough? Almost zero, right? But now we're interested in, well, okay, maybe I know it's not exact, but now how close is it? How can I quantify how accurate it is, right? So really, we really want to know what the dynamics of this are. Like, in other words, if I take a number like blood pressure in Brooklyn, the blood pressure, if I take 100 blood pressures, well, they range from, those 100 people I took at random range from 95 to 110, whatever it is, millimeters of mercury, whatever the measure is, right? They range from 195 to 110 or something like that. And the average came out to be 99.7, right? Well, the range of those numbers weren't very variable, right? But now I go to Staten Island and I do the same thing, and I take 100 people, but the variability is, you got people from 80 to 120. The numbers are very variable, right? Now, when I get the average, I get 99.7 also. There also. Which of the two of those do I have more confidence in? That's the real middle. Which would you say I have more confidence in? Well, the one in Brooklyn seems to be like a much narrower spread. It's much less variable. So I might have a little bit more confidence that my middle there is really close to the middle for the population. But in Staten Island, the numbers are much more variable. So maybe I have less confidence there, right? So there's something going on here between the sample size that we take and the variability of the numbers that tells us something, that's going to be able to tell us something about how much confidence that we can have when we take a sample from a population, and how accurate that might be in terms of really predicting the mean of a population, for instance. Okay, or the percent. If it's a binomial, like whether or not some people have diabetes, whether or not we got the percentage right, the prevalence right, and so on. We're going to do an exercise here, and in this exercise, I have if you open up a document, the Word document, you'll notice that I have 100 numbers. The numbers I'm talking about, the ones that are in black here, in between the ranges of numbers on the columns and the rows here, which are in red. Now, I believe if you go back into Blackboard, there's also an Excel sheet. That's the same thing. That's the same distribution in numbers. Now, I'm going to use that Excel spreadsheet just the same way that I would use, I'm going to use this range of numbers. Just say I would use rows and columns when I'm describing a location, a cell on a spreadsheet, right? So if I'm going to start with the rows, and then I'm going to start with the first digit of the rows, second digit is the column. So in other words, if I told you 00, it would be the number 61. If I told you 225, it would be the row 2, column 5 would be the number 46, right? And if I told you 72, it would be row 7, column 2 would be the number 41. Now, I'm going to have each of you randomly select 16 numbers from this page. So how are we going to do a random selection? Okay. Well, I could tell you to just put click, put your finger down randomly around this page, right? Except the guys that are right-handed are going to pick more numbers on the right side. The guys that are left-handed are going to pick more numbers on the left side. Or you're going to have some sort of it's likely you're going to have some sort of pattern to the way that you pick. Maybe your hand's a little heavy today. You might pick the lower numbers. You're feeling a little bit more energy. You might pick there might be some pattern to it. So we need a way to ensure that our selection of people from this population is truly random. Well, as it happens in your textbook and many other textbooks, there are random number tables, right? There's other ways to do this. You can use computers to generate random numbers. There's a lot of other ways to do this. But if you look at another document that's under session 5, there's something called a random number table. Okay, and here it is. You got a description of what it is here and how to use it and so on and so forth. But here's a table right here. They have generated, either using a computer or some other kind of device to do this, they've generated random numbers. 1, 1, 1, 6, 4, 3, 6, 3, 1, 8. It doesn't look random, but trust me, they've generated. And things that are random tend to cluster anyway every once in a while. So even though I see 3 1s in a row right off the bat, doesn't mean that they didn't come up randomly, those 3. Although it's like 1 in 100 that they would 1/10 times 1/10 is pretty uncommon. You would get 3 1s in a row, right? But 3 same numbers in a row would be 10 times that. But that's neither here nor there. I wouldn't overthink it. Let's assume that these are random numbers in here. So in order to identify a person, I would pick out. I'm going to start from anywhere you want in this random number table. It's got a bunch of pages here. Start from anywhere you want. I'm going to start from right here. My first person is the person number 80. My second person is going to be the person number 01 or number 1. Next person is going to be the number 88. Next person is going to be number 47. In other words, row 4, column 7. So I want you guys, for instance, 80. My first person is 80. I'm going to go to this chart. I'm going to go to row 8, column 0, and that's the number 54. So I want you guys to do that for 16 numbers, each one of you. Just start in a different place. Start anywhere you want in this random number table. Don't start in the same place I started. 16 numbers. Okay, and you can, somewhere else on the Excel spreadsheet, you can write those 16 numbers in the column, and we're gonna do some statistics with them. Okay. Okay, and in the meantime, while you're doing that, this is our population. You're taking a sample of 16 from our population, right? Our population is actually 100 people. So I'm going to take our population, and I'm going to figure out what the mean of our population is. Okay, so our mean is going to be equal to the average, parentheses, of all of these 100 numbers. And I'm not going to do it now. I'm going to wait until you do yours. I don't want to bias you. So I'm going to wait until I start getting numbers from you. So as you do your 16 numbers, add them up and give me the average of those 16 numbers. If you're really allergic to that table, you can. I'll let you go ahead. You can use your finger and randomly select them if you want. But I would prefer you use the table. Okay, you guys at home can do this too, I hope. Is that clear? Guys at home, is that clear to you guys what I'm trying to do here? Actually, I'm going to start with minimum. Okay, good. And whenever you're ready, you can just start yelling out numbers to me. I like doing exercises like this because I get to drink my coffee a little bit while you guys do all the work, catch my breath. Okay. Okay. Got anybody yet? What's the number? The mean, the average. I want you to find the average now of your sample. I want you to find your sample average. What do we call our sample average? Mean, but we instead of using mu, we use x bar. X with a bar over the top of it. And you can either add them up and divide by 17, or you can use the average function in Excel. Okay, 52.2. I'm going to round it off to the nearest decimal place. Oops. 27.3? Oh, well, I'm sorry. Yeah, that sounds better. 54. Okay. What's the mean? Yep, the average of your 16 numbers. Okay. Sure. Oh, you can. Oh, you're writing a script to do them all, do it over and over again. You can give me a bunch of them. Are they going to be really random? Okay, good. Give me a few. Yeah. 40. Oh, wait. 49.2. 49.14. How are the guys? Oh, I'm getting a few online too. Let me get the guys online here so I don't forget about them. 54. Wait. Let me get the guys online. 47.4. 49. 51.8. 51. Oops. Another 51. Okay, what else? What are the numbers they get here? Yes?
52.3.
52.3. Okay, and give me one more.
47.1.
47.1. Did I hear another one there? 49. Okay. All right, I think that's enough for now. Okay? Maybe one more so I have an even number. 46.3. Okay, good. Let's stop. That's enough, guys. All right, so now each one of these are we randomly sampled 16 people out of 100, so they're approximations of the mean of this population. So let's calculate the mean of this population. First of all, the minimum is, oops, the lowest number in here is 27. The biggest number in here is 69. The range is equal to 69 minus 27. 42. The mean, by looking at those numbers, you can probably pretty much guess what the mean is going to be kind of like, right? It's going to be 50. Means 50. And the standard deviation is equal to standard deviation is equal to, see what it is, 9. So the population mean is 50. The population standard deviation is 9. The spread and the standard deviation gives us a measure of spread, right? So now let's take a look at these numbers that we wound up here. Now the range of all these different numbers was very wide, 27 to 69, really big range. But when we took a sample of size 16 and took the average of each one of them, now look what happened to the range, right? The minimum was 46 and the maximum is 54. So it's much, the means themselves, the means of our samples are much more narrower. This range is much narrower than the means of the actual population. So let's think about this. What if I take repeated means, if I calculate them over and over and over again? What's going to happen to the standard deviations of those sample means in relation to the population mean? I'm going to actually calculate the mean of our mean of all of our samples equals average, parentheses, and the average of all these means is equal to, well, look at that. It's almost equal to the same thing. You know, there's decimal places that I'm not accounting for, but the mean is equal to pretty much rough. It's a much better predictor, all of these together. What's the standard deviation? What was the standard deviation of the population? The actual values, it was 9. What do you think is going to happen to the standard deviation of the sample means now? It's going to be a smaller number than because they're not spread out as much. So let's find that this is our mean for x. Let's find out what our standard deviation for our population is, for our samples is. It's equal to the standard deviation of all of these values here, the variability of all these values here. And it comes out to be 2.41, right? Much narrower. The bigger the sample size is, the much narrower is going to be our spread. In other words, if we had taken sample size of 25, all of the values would have been closer to 50 than these. If I'd taken sample size of 4, then we would have had much more spread. The sample size is related to the standard deviation or the spread of the samples is dependent on the means of the samples is dependent on the sample size. Okay, to make a long story short, the standard deviation for the sample means, right, is equal to the standard deviation of the population divided by the square root of the sample size. Let's think about that. Whoops. I should have put a little space up there so it didn't do that to me. Shouldn't put the equal sign in there. Okay, there we go. Is equal to is equal to the standard deviation of the population. In our case, the standard deviation was 9. The sample size was 16. So that's 9 divided by 4. So theoretically, if we took thousands and thousands or your millions of sample means of size 6, samples of size 16, took the averages, the standard deviation that we would wind up with is 9 over 4, the square root of 16, or about 2.5. 2.25, excuse me. We wound up with 2.41. We're actually pretty close. Why is this important to us? Because now we have a way of understanding how far we might be from the true mean, right? Anybody remember the idea that rule that we had about 95% confident, 95% of the outcomes is within 2 standard. If it's a normal distribution, it's within 2 standard deviations. 95% of the outcome. So 95% of the samples that we would take from this population are going to be within 2 standard deviations of the standard deviation of the sample means, right? In other words, 95 between 2.25 of 4.5 below and 4.5 above. So we have an idea of where we would expect samples, or how variable we would expect samples to be. Okay, we're going to put that to work in a little while to help us understand that if we take a sample, what we can rely on that sample for and what we can't rely on that sample for. Okay, good. Let's take a look at what we have here. The real story coming out of this is that bigger the sample size is, the closer that you're going to be, the closer you're likely to be to the true population mean, but also if you took many samples, the less the variability would be from the sample mean, from the population mean. Okay, all right, let's take a look at an exercise here. Now, this is just to remind us of what we were doing with the normal distribution before. Total cholesterol values for a certain population are approximately normal, distribute a mean of 200 and a standard deviation of 20 milligrams per 100 milliliters. Find the probability that an individual picked at random from this population will have a cholesterol value between 180 and 220. Okay, now, am I talking about a sample here or a population? Population, right? You don't see a sample size there, right? I'm talking about the entire population. The total cholesterol values is an average of 200 with a standard deviation of the population of 20. So 180 and 220 are one standard deviation below the mean and one standard deviation above the mean for the population. So what percentage of individuals will we expect to be in that range? Do you remember? 68%, right? Let me just draw right, here's our standard normal distribution. Our mean was 200. Our standard deviation, sigma, population standard deviation is 20, right? So 180 to 220, it's going to be one standard deviation below the mean, one standard deviation above. So this is going to be 68% of the population is going to have a cholesterol level between those two numbers, right? So if my probability of randomly selecting, right, one person out of it that has a cholesterol in that range is going to be 68, since 68% of the population has that cholesterol. Okay, you guys online are okay with that? Yes? And between 160 and 240? 95. Yeah, 95%, right? Because that's 2 standard deviations below and 2 standard deviations above. So Now we're talking about 95% of the population and 95% chance that that individual we pick is going to be in that range. Greater than 225 milligrams per liter. Okay, it gets a little bit more complicated here. Here's 220, greater than 225. Okay, it's going to be this area right here, right? So how do we calculate that? Well, we got what's going to be x minus mu over the standard deviation. That's our z-score. It's going to be 225 minus 200 over 20 is going to be 25 over 20, or 1.25. So our z-score is equal to 1.25. So what's the area here? Yeah, a couple of ways I got to look that up, right? A couple of ways I can do that. One way is I can go to our z-table. I could use my Excel spreadsheet, or I can go to my z-table, which I think I gave you one. Whoops. It's already open. Yeah, let's take a look. Okay, so 1.25, positive 1.20, 1, 2, 3, 4, 5. What'd you say? 89.44. I'm going to round that off to 89.5 for our purposes.
You got minus 1.
Right, because that's going to give us the area to the left of that z-score. We're interested in the percentage of the population that's above that z-score. So if it's 89, where did I go over here? So if that's 89.4, if this area to the left here is 89.4, that's going to leave 10.6% of the population above that. And the probability of choosing one individual that's 225 or higher is going to be 0.106. Okay, next version of this. Now I'm getting things are getting crowded over here. Okay, I can do it this way. Good. Okay, less than 150. Again, this is kind of a reprise of what we've done before. Okay, less than 150 is going to be, this is going to be 180. This is going to be 160. So less than 150. 150 is going. This is going to be 180, right? One standard deviation. Two standard deviations is going to be 160. So 150 is going to be way down here, right? So that's going to be a pretty small area, right? So let's see, 150 minus 200 over 20 is going to be minus 50 over 20. So this z-score is equal to negative 2.5. Right? So let's look that up. Negative 2.5, and we can already see it's going to be a small value. Negative 2.50 is 0.006. It's less than 1%. Right? This is going to be 0.006, or in other words, 0.6%. Right? That's our probability. This is our percentage of the distribution. So the probability of picking someone out from this population that has a cholesterol less than 150 is less than 1% chance of that occurring, 0.06 of that occurring. Okay, let's try the next one. Between 190 and 210. Okay, now I'm going to redraw this a little bit because it's getting ugly. Okay, here we go again. 200. Okay, sigma is equal to 20. And we're going to 190. And what did I say, 210? Okay, 190 and 210. And we said less than or greater than? Is that what I said? Or is it in between? Between. Okay, between. Okay, so we're looking for that area in between. Well, I know that whatever I'm going to do with this table is going to give me an area to the left of that. So what I'm going to do is I'm going to find out what the z-score is for 210. It will give me the area to the right, to the left of that. Then I'm going to find the area below 190, right? And I'm going to subtract this area from the larger area, and it's going to leave me with the area I'm interested in. So let's figure those z-scores out. X, C minus mu over sigma. Okay, it's going to be equal to, for 210, it's going to be 210 minus 200 over 20 is equal to 0.5. And z-score for 190 is going to be equal to 190 minus 200 over 20 is going to be equal to negative 0.5. Okay, so let's find those areas. So the first area, the plus 0.5, 0.05 is going to be 0.6915. 0.6915, and that's going to be the whole area to the left of 210. And now negative 0.5, okay, is going to be 0.3085. This area in here is going to be 0.3085. So the area that's left over, if we subtract that 30%, it's going to be 0.6. Something happening behind me? Where's, oh, that's the printer. Okay, what's that going to be? It's going to be 5, 1, oh, I screwed this up. 5, carry 1, 8, 3, 8, and 3.3. Did I get that right? 38.35, 0.385.
38.
Yeah.
Sorry, 38.
Okay, yeah, it's close enough. Okay, so about 38% of this population is going to be between those two numbers. Nothing new, right? Just a way of using nothing that we haven't introduced anything new because we're dealing here with the population. So we're using this table just as we have always used this table for normal populations that are normally distributed, figuring out what we can about that distribution. Okay, let's move on from that now. Okay, now this idea of if we took repeated samples from a population, the sample results would all approximate the mean, right? In other words, we would expect, I would take a sample, would take 25 people from a population. We find the average of those 25 people, it's going to kind of approximate the mean. May not be exactly the mean, it's going to kind of approximate it. Certainly going to be a better approximation than just picking one person out at random. And the bigger the sample I get, it's kind of intuitively, you can say to yourself, bigger the sample you get, if you take a sample of 100 people, probably going to be a better approximation of the mean than a sample of 25 people, right? But now, the really interesting thing about this is if I did this many, many, many times with a certain sample size, we now know something special about the way all of those repeated samples are going to distribute themselves. They're going to have a standard deviation. All of those repeated samples of that size, they're going to have a standard deviation which is related to the sample size that we took, with the population sample size and the sample size that we took. The population standard deviation and the sample size. In other words, the standard deviation for these sample means is going to be equal to the population standard deviation divided by the square root of the sample size that we use. Since the sample size is in the denominator, the bottom of the fraction, the bigger the sample size is, the smaller is going to be our standard deviation for all of these sample means. So a big sample size means that these numbers are much tighter. We have much more confidence in the means that the sample means that we get, right? That's going to be closer to the real mean. So that's going to be an interesting tool for us to use. Okay, that is called the central limit theorem. There's some other elements of the central limit theorem that probably came up in the lecture. Certain things about like sometimes you can do this with sample means from a population where the population itself is not exactly normal, but then when you do these repeated samples, the distribution of the sample means is normal, right? Kind of like gives us a real tool to work with here in terms of understanding how these samples work. Okay, so let's take a look at this. A sample of size 25 is taken from the population that we just looked at above. What's the probability that the mean of that sample, mean of those samples, is larger than 204? That the mean of that sample, we're going to take a sample of size 25, right? We're going to take one sample from that population. What's the probability that the average for that mean that we calculate from that sample of 25 is greater than 204? Well, things have changed a little bit, right? Now let's take a look at this. First of all, number one, we know that if the population mean is 200, right? Then if we take samples over and over again, we would expect the average of all of those sample means to be 200, right? Let me undo this. Okay, why is it not doing? Okay, doesn't want to undo for me. Let me get another page. Okay, our population looks something like this. Okay, and it had a mean of 200. Now that we're taking a sample from it, and we're taking repeated samples over and over and over again, and we're now drawing a new distribution which represents all of those sample means, it's going to be, half of them are going to be under 200, half of them are going to be over 200 just by chance if I take enough of them. But the distribution of all those sample means is going to be narrower. It's still going to be centered around 200, but it's going to be a narrower distribution. Okay, how much narrower? We're about to find out. Okay, so let's take a look at what our standard deviation should be. Our standard deviation of our population was 20, right? And our sample size is equal to, what I say it was? 25. So now what is our standard deviation for our sample means? Standard deviation for our sample means is going to be sigma over the square root of n. Okay, population standard deviation 20 over the square root of the sample size, which is 5, it's going to be equal to 4. So our standard deviation for our sample means is equal to 4 because the sample size is 25. Okay, now let's think about that for a second. Now this 4 represents not the standard deviation of the population, but the spread or standard deviation of repeated samples from the same population of size 25. I want to give this a new name so I distinguish it from the population standard deviation. You guys will, if you guys listen to the lecture, what's the name that he gave it? You remember? Standard error, right? From now on, we're going to call that the standard error. But we know that really what it is the standard deviation of repeated samples of the same size from a population. That's going to be called the standard error. So our standard error is equal to 4. Okay, and we're going to use it just like a standard deviation. Right now we're about to use it. Okay, so what's the probability that the mean of the sample, well, first of all, before I ask that, what's the probability that if you took a random sample of size 25 from this population, that the mean of that sample would be greater than 200? 50%, half the time, right? What's the probability to take a sample size of 25 and what's the probability to be less than 200? 50%. It's going to be true for any sample size because it's half the time it's going to be above the mean, half the time it's going to be below the mean because you ran sampling for that population randomly, right? So, but now once we want to get into a real idea of what's the likelihood of getting other values from this population, well, now things get a little bit more complicated. What's the probability that the mean of the sample is larger than 204? Okay, so here's 200, and 204 would be about here. Well, let's see. One standard error above the mean would be 204. Two standard errors above the mean would be 205, 208. One below would be 196. Two below would be 192. Remember this? Remember when we looked at this population? What was two standard deviations below the mean for the population? It was like 160. Now, two standard deviations for the sample mean of sample size 25 is only 192. It's much tighter. These various all of these collected means are much closer together. Okay, so let me read this again so I don't get it mixed up. Okay, what's the probability that it's larger than 204? Okay, well, 204 is one standard error above the mean, right? So what's that area in there? Well, we know this, the area between 196 and 204 is going to be roughly 68% of the sample means are going to fall within 196 to 204. So this is going to be about 34%. So that's going to leave about 16% of the sample means will come out higher than that. If we took a sample size of 25 repeatedly over and over again, 16% of the time they'd be over 204. That's sample means now, right? So we're starting to see a pattern here. How sample means distribute themselves based on the population standard deviation and the sample size. We only really need to know two things about how they distribute themselves: population standard deviation and the sample size. Sample size is easy. You're controlling the sample size. Population standard deviation is a little bit trickier. For the moment, for this session, for the rest of this session, we're going to assume that we know the population standard deviation. Is it likely that we'll really ever know the population standard deviation? No, right? Because we're not going to sample the entire population. We're going to have to wind up guessing at it. That's going to add another layer of uncertainty. We don't want to introduce that right now. We're going to assume that somebody's told us what the population standard deviation is. Maybe someone did another study where they took a really large sample or something like that, or we have some other reason to assume it's a certain amount. We're not going to bother with that right now. Okay, let's continue to answer another couple of these questions. Okay, what's the probability that the mean of the sample is between 192 and 204? Well, that's an easy one because 192 and 204, a little less than an easy one. Okay, so 204 to the left of this is going to be about that's going to be 84%. Okay, I'm going to call it 84% because I call this 16. See, I could go to the table and do this, right? Right, but I'm just using, like our estimates here. 84%, and below 192, that's two standard deviations, about 2.5%. Right, so that the area between these two is going to be 84 minus 2.5, or say roughly 81.5%. Okay, the next one I'll actually use the Z table on. Okay, if there is another one. There is. If we took repeated samples of 25 from this population, what range would we expect 95% of the sample means to fall in? Using the empirical rule and then using the Z table. Okay, so we're going to take, okay, again, a fresh piece of paper here. Okay, here is our distribution. Sample, the population mean is 200. Right? Our standard error we calculated already because the sample size was 25 and the standard deviation of the population was 20. We found calculated standard error came out to be 4. Within what range of numbers would we expect 95% of these outcomes to be for a sample mean for this population? We'd expect to be 2 standard deviations below and 2 standard deviations above. If I use the empirical rule, what is this number? 192. Yeah, and the other one would be 208, right? Let's use the Z-score for 95%. Okay, so now if I go to the table, I actually have to look up, let's see, for over here, so 2.5% is going to be on this end of the distribution, and 2.5% is going to be on this tail in the distribution. So if I want to do this more accurately, I go to the table, and I'm looking for a Z-score which represents 2.5% of the population to the left. So I'm looking for an area in the middle here of 2.5%. So I'm going to scout around here 2.07, 2.0, 2.0, 2.17, 2.22, 2.2. Here we go, 2.50. That looks like a Z-score of negative 1.96. It's not 2, right? It's really 1.96. In other words, it's nice that we have what we call the empirical rule, that estimate. I just did something nasty to this. What did I do? Okay. Come on, come back. Oh, maybe this. Yep, that's it. I think. Yep. Okay. The empirical rule tells us that 95% of the population is between 2 standard deviations below and 2 standard deviations above. In truth, it's really 1.96 standard deviations below and 1.96 standard deviations above. Right now, we just demonstrated it with the low end, right? So what would that value be there? 1.96 standard deviations below the mean. Okay, well, let's see. X bar or mu, either one. A mu, let's say, is the mean, right? Minus 1.96 times the standard error, right? So 200 minus 1.96 times the standard error. So 4 times 1.96 is how much? Okay. 1.96 times 4 is equal to 7.84. right? And I'm going to subtract that. Press quit. I'm going to subtract that from 200. And it comes out to 192.16. Not exactly 192, but 192.16. So 192.16 instead of 192. Okay, let's do the same thing at the top. Well, now I'm looking for the area where 97.5% of it is below that value. So I'm going to go back to my Z table, go to the positive side, and look for 1.96 on this side. I mean, 97, well, I gave it away, didn't I? 97.5 on this side, which is a Z-score of, again, 1.96, as you can see there. So on this side, right, 1.96, I'm taking 1.96 times the standard error, which again, in my calculator, is probably still there in my calculator. This time, I'm going to be adding it to the mean, right? So I'm going to clear that. So the mean's 200 plus 7.84, 1.96 times 4. Comes out to 207.84. So that's really that's a really more accurate result. 20, what did I say? I forgot it already. So 207.84, yeah. Okay, so that's a more realist, that's a more accurate measure of what the real range for 95% of the population is. And I don't know, maybe the next problem actually may have us do it again. Do another version of that. I'm not sure, I don't remember what else was on there. Okay, a sample size of 100 is taken from the same population. And within what range would we expect 95% of the sample to form? First using the empirical rule and then using the Z table again. Okay, let's do it again for a population size of 100. What's going to change a sample size of 100. What's going to change now if the sample size is 100? Is the mean going to change? Mean of repeated sample? No, mean's going to stay the same. Right. The standard error actually is the standard deviation of the population stays the same, still 20. But the standard error, the standard deviation of the means now is going to be equal to 20 over the square root of 100, which is going to be equal to 2, right? 20 divided by 10. So now if we're looking for 95% of the population, of 95% of the possible means that we might get if we took a sample size of 100 from this population. Now, using the empirical rule, it's going to be 200 minus 4, which is going to be 196, and 200 minus plus 4, which is going to be 204. Okay, 95% of the possible outcomes for taking a sample size of 100 from this mean. So now if I really wanted to do that more accurately, I would say 1.96 times 2, right? And add and subtract that from the mean that I have. Okay, 200 plus 1.96 is 3.894, 92, right? And 200 minus 3.92.
Can we go back to why you didn't choose 1.96?
1.96?
Yeah.
Because when the table tells me that we use the empirical rule that says 95% of the outcomes from a normal distribution are going to be between 2 standard deviation below and 2 standard deviations above the mean, 95% of the outcomes, whether it's sample means taken over and over again, or even the population distribution, is going to be between 2 standard deviations below, 2 standard deviations above. That's only an estimate. The true number is 1.96. And how do I know that the true number is 1.96? Because if I really want to find 95%, the middle 95% of the population, right? That means that 2.5% are going to be in the bottom tail outside of that, and 2.5% are going to be in the top tail outside of that. So now I can go to my Z table and look up what the Z score, the number of standard deviations, really has to be in order for me to get 2.5% in this tail, right? And we know if I went there and I did that, the area that would give me 2.5%, turns out to be not 2, right? The z-score that gives me that area turns out to be not, oops, I got the wrong one. Where is it? Where'd I put it? Oh, it's under the Word document. Okay. There it is. Okay. If I go here and I look for these are all the areas that relate to the z-scores. A lot of times I'm using the z-score to find the area. This time I'm using the area to find the z-score. So if I look in here, if I look for 2.5%, remember these are the areas. This is the area I'm looking for to the left of that. The z-score that gives me 2.5% is the z-score that's represented by 0.0250. This is 2.5% right here. And what z-score represents that? Not 2, but 1.96. See, 2.0, 2 standard deviations, really is a little less than 2.5%. So that's that. Remember, the empirical formula is just an estimate. It's just a quick estimate.
So wouldn't it go better?
What's this? Oh yeah, it's better to use the. In fact, for the rest of the time, once we get past this, the rest of the time you're going to be using the tables or Excel to calculate your areas and your probabilities and so on and so forth, right? The empirical rule was just a introduction. However, the empirical is also a good tool anyway, because whenever you do any of this stuff, you can sketch it out, read the problem, and estimate it using the empirical rule and say, gee, it looks to me like it's going to be 25%. And then if you do your calculation and it comes out to be 42%, you say to yourself, something looks a little fishy to me. Maybe I made a mistake in my calculation. So it gives you an opportunity to kind of estimate it first if you want to, or do the problem and then go back and estimate, do the problem, and then just check yourself, do it with the empirical formula to see if the areas look right to you, look correct to you. Yes.
So when you say within what range would
Oh my God, you just brought something up that's really important. You don't even know you did it yet. Okay? You're talking about ranges and stuff like that.
Yeah,
and
so is that similar to what we've just been doing though, where we take one piece, like we're doing the range where you're subtracting one part.
Yep. And that's really important stuff, because the next thing that's going to come up here is how we're going to use this effectively. Okay, so that involves some of that. So you got a little